Okay, and so let's start with the presentation of Stefan about lepton number violation in colliders via heavy neutrino and antineutrino oscillations. So we are happy to have you here, Stefan, and please, you can start.
Yeah, thank you very much. It's my pleasure to be here and talk to you about this topic. And of course, the motivation to study heavy neutrinos or heavy neutral leptons is that they might be indeed the an explanation of the puzzle why the neutrinos have mass. So they might, in a sense, be the missing piece of the standard model to explain this. And I will use in the following like sterile neutrinos or right-handed neutrinos or heavy neutrinos kind of as synonyms for fermions, which are simply completely uncharged under the symmetries of the standard model. And as this diagram here shows, such particles do not exist in the standard model, but if we would introduce them, we would get two extra terms in the Lagrangian in addition to the standard model. And the first one would be a Majorana mass matrix for these right-handed neutrinos. And the other one would be a neutrino-Yukawa coupling them to the Higgs and to the lepton doublets. So as you of course all know, if we would have these extra terms, then one would obtain a mass matrix for the light neutrinos via the CISO formula, so which is shown here. It is inverse proportional to the mass matrix of the right-handed neutrinos. And from this light neutrino mass matrix, one can now explain the neutrino data that we have from the light neutrino flavor oscillations. And of course, we have to explain two mass splittings. So we need at least two of the light neutrinos being massive. And from this, we already know that we need at least two sterile neutrinos, two right-handed neutrinos, in order to have a rank 2 for this light neutrino mass matrix. So this is already a minimal thing we can already tell from the CISO formula. So here comes an outline of my talk after this very brief motivation. So in the first part, I would like to argue that the models of neutrino mass generation that you can actually test at colliders are models where these sterile neutrinos form pseudo-Dirac pairs of heavy neutrinos. So these are scenarios where you have the lepton number as an approximate symmetry, so it's only a small violation in the Lagrangian, and where two of the sterile neutrinos each form pairs where they only have a small mass splitting and very similar couplings. Okay, then I would like to talk a bit about constraints on the heavy neutral leptons, on the sterile neutrinos, and also about future sensitivities for discovering them at future colliders. And then I would like to come to the main part of my talk, which is that in this scenario of pseudo-Dirac pairs of H and Ls, that one can understand lepton number violation there by the phenomenon of heavy neutrino-antineutrino oscillations. And of course, lepton number violation is crucial if you would like to link an observation of heavy neutral leptons to erosion of neutrino masses. And that's why it is an important subject to consider, I think. So within my group, so we had some intense research work on this subject, and I listed some of the references here. For instance, we were looking at this heavy neutrino-antineutrino oscillations in a quantum field theory formalism, which is important also to look at decoherence effects and next to leading order of these oscillations. We proposed a benchmark scenario for studying it at Collider, which is pretty simple and can be easily used. We also released a matgraph patch because in the standard matgraph one cannot simulate these oscillations. So we have a description how to include them in Collider simulations. And we also used this recently to show that one can resolve these oscillations at the high luminosity LHC, at least for some example benchmark points. We also discussed decoherence effects, and we very recently looked at the oscillations at a future FCCEE. And these works, where I'm going to also tell you about it in the remainder of my talk, are mainly done with my student, Johannes Roskop, with Jan Heyer from Lisbon, and also with a master student, Bruno Oliveira, at least the last work on FCCEE, who is also from Lisbon. All right, so let's get started with the landscape discussion that I was announcing. And for simplifying things, I would like to discuss the case of what? I was jumping forward. So of having two heavy neutral leptons, two stable neutrinos. And now in the mass basis, one has the following terms in the Lagrangian. So the first two terms here are the Dirac mass terms, where the Dirac masses here are the Yukawa couplings times SVEF over square root of 2. And then we have the two masses of the two heavy neutral leptons, the two stereo neutrinos. And with the CISO formula, one gets two contributions to the light neutrino mass matrix. One is proportional to the MD1, so the Dirac Yukawa couplings to the first right-handed neutrino mass eigenstate, and suppressed by M1, and the second one analogously with the second right-handed neutrino. So, and now with these two contributions, we would like to understand the smallness of the observed light neutrinos. And there are three limiting cases. So one can present this in a triangle shape, the landscape of possible models, which is shown here below. So you can see at the upper peak of the triangle, this is the high scale CISO. So this means one can explain the smallness of the light neutrino masses by just choosing some large M1 and M2. So a large denominator in both of these terms would make them small, and then neutrino masses are small because these Majorana masses of the heavy neutral leptons are large. This is the high scale CISO. But of course, if we are plug in numbers, then there we are typically around the grand unification scale in the extreme limits, and we cannot test such high scales at colliders, of course. And on the opposite side, you have the low scale CISO models where you're at much lower energies. So this is this lower, the baseline of this triangle, more or less. So now the other limit on the left side, this is the small coupling regime of the CISO mechanism. So you have Yukawa couplings much smaller than 1. Then you explain the smallness of the neutrino mass matrix by having a small numerator of both of these terms. Small Yukawa couplings giving you small Dirac mass contributions here. And this is one possibility. But again, these couplings here would be so small that actually you cannot really produce them effectively at colliders. And this is also at least very difficult to test. So at the high luminosity LHC, you will not have really events when you are in this extreme small coupling limit, and you have heavy neutral leptons with masses around the electroweak scale. And maybe at the FCCEE, you might have a few events and you come into this region, but then also with this, you cannot really do good statistics and probe this very well. So also this extreme of this triangle, the left part, is not really well testable. But there is a third logical possibility, and that is that you have these two terms, but these two terms almost cancel each other. And of course, this would be just an artificial fine-tuning. It would not be interesting and would not be talking about it. But this cancellation can be justified and can be explained by an approximate symmetry. So it should be an almost cancellation to get a small light neutrino matrix. And it could come from a symmetry that is only slightly broken, so an approximate symmetry. And this symmetry is as simple as an extension of the standard lepton number that we have in the standard model. So, and this part where you explain the small neutrino masses by an approximate symmetry, this is the region of this landscape where you can actually test these models at colliders. All right. So let us look at this in a bit more detail. So at this symmetry protected regime, you have an approximate lepton number symmetry, but let us start with an exact symmetry. And that could be really just the extension of lepton numbers. So you could give the lepton doublets, the lepton number 1, the first right-handed neutrino also lepton number 1, and the second one lepton number -1. And then you write down all the allowed terms in the Lagrangian, so these extra terms with the heavy neutral leptons. And then you arrive at these terms, these two terms that are shown on the right. So you have a mass matrix, Majorana mass matrix, but this only has off-diagonal terms. So only coupled on the n are 1 and the n are 2. Because everything, so the other terms are forbidden by this lepton number. And also when you look at the Yukawa matrix, then you see only the NR1 can have Yukawa couplings. So you only have one column of entries here because the other one has the wrong lepton number to write down a Yukawa coupling. So if you have this, then you can check in the symmetry. This is we call the exact symmetry limit. Then the light neutrino masses are 0. So you can check this explicitly, but it also have to be because the lepton doublets now have a lepton number and there are no light Majorana masses possible. You can also write this in the mass basis of having the left chiral neutrinos and the right chiral neutrinos. And here, this is shown also here below. In this notation, so I suppressed the 3 indices or the 3 versions of the left chiral neutrinos. So this MD, for instance, this is a column with 3 entries. So take this into account. So we are representing this here as a 3x3 mass matrix, but it is actually a 5x5 one. And with the structure, yeah, you get 0 light neutrino masses. The heavy neutrinos you get when you diagonalize this part here, and they are exactly degenerate. In this situation, you can also write these 2 Weyl degrees of freedom, Weyl spinor degrees of freedom into a Dirac spinor, and then this mass matrix shown up here, so this off-diagonal Majorana mass matrix would be just the corresponding Dirac mass term. So this is also the limit where you combine the 2 HNLs into an exact Dirac HNL. Okay, so now for comparison, let's look at the most general mass matrix, 5x5 mass matrix here, or in our notation 3x3, where all the entries filled that are allowed by gauge symmetry. So the 0, 0 here would not be present at tree level, but you can now have also Dirac, Yukawa, well, kind of Dirac masses with the second right-handed neutrino, and the whole right-handed neutrino mass matrix is filled. So if you plug in some arbitrary numbers here, you would get 2 Majorana HNLs out there, which have a large mass splitting. But then when you do this, you find that you either produce 2 large light neutrino masses, or you have to be either in the high scale regime where this M is very large, or in the small coupling regime where the MD are very large. Otherwise, you do not get the smallness of the light neutrino masses. So these are the 2 examples, well, in this landscape, which you cannot test very well at colliders. Now, the third possibility, when you have this approximate symmetry protection, then you would not have an exact Dirac HNL, but you would have small perturbations here. So this is shown in this green box at the bottom now. So these epsilons here, when you introduce them, small compared, so the epsilon prime, epsilon double prime to the M, and this other epsilon here, small to the Dirac mass contribution, then you have perturbed the structure, the symmetry is slightly broken, and you will get small neutrino masses out of this proportional to these epsilon entries. So when the epsilons go to 0, then neutrino masses would also go to 0. So in a technical sense, you have a natural explanation of the smallness of neutrino masses by when the symmetry is getting exact, then these small parameters go to 0 and the neutrino masses become 0 again. But having this slightly broken, you explain the smallness of neutrino masses. And what you also introduce is a small splitting between the 2 HNL masses. So this is this delta M here, this delta M parameter. And in this case, we call this a pseudo-Dirac pair of heavy neutral leptons. And this is the scenario which I'm going to focus on in my talk. So on this transparency, you have a bit more details about the different models that one can have. In this case, so one can distinguish them by the types of perturbations one introduces on top of this symmetry limit. So, for example, if you introduce extra Dirac masses with the second right-handed neutrino, so this epsilon here on this example on the most left. Then one is calling this a linear seesaw mechanism. You have light neutrino masses that are proportional to this epsilon times md over m. And in fact, so these are 3 entries that you can introduce here. So remember, this md is a column of 3 entries, and this epsilon also. And you can, with this perturbation, already explain the complete neutrino data. So you have 2 light neutrinos that can be massive, and you can explain all the mixing angles and CP phases from that. And if you assume that you only have this one pair, this one pseudo-Dirac pair with this particular perturbation, then you're also very predictive on how large this mass splitting of the HNLs is. And you can express it fully in terms of the mass splittings of the light neutrinos. And so for the normal ordering, a normal hierarchical case, or the inverse hierarchical case, so in fact you have, well, 2 of the light neutrinos are massive, so this means you have the lightest of the light neutrinos is always massless, so you have strong hierarchies, and these are the 2 values that you can get for the mass splittings. There is also another case where you introduce a perturbation in the mass matrix of the right-handed neutrinos. So this is the inverse seesaw case. And when you do this, you in this for one pseudo-Dirac pair of HNLs, then you get 1 massive light neutrino only. So this is why in these models you typically have 2 or 3 pairs. I think normally you even introduce 3 pairs of HNLs, because from one of them you only get 1 massive light neutrino. And then the neutrino masses are given by this formula here. And you also get an expression for the mass splitting in terms of the light neutrino mass that you generate over, so this theta square parameters. I'm going to introduce this on the next transparency, the active sterile mixing angle. And theta is kind of the Dirac mass over the Majorana mass in a sense. And the third type of models you get when you introduce a extra term in the mass matrix of the right neutrinos in this 1-1 position. So that's the example on the right. And with this, you do not produce a light neutrino masses at tree level, but only at loop level. But nevertheless, also this epsilon here cannot be too large because you have an extra suppression 1/16 pi squared, but still you're producing neutrino masses that are proportional to this epsilon parameter. And a lot of studies have been done for these low-scale seesaw models of this type. So it's quite common. And also here at your institute, recently there has been a detailed studies of these, also sometimes called quasi-Dirac neutrinos. And yeah, so there exist many model realizations and also discussions of this. So what we did some time ago in order to make this a bit simpler, because there are also many parameters you can introduce and there are many pairs of HNLs that can exist, we tried to formulate a benchmark model for collider studies where we wanted to focus on a dominant pair of pseudo-Dirac HNLs. And the leading structure that we assumed is the one that is shown here in this green box. It is basically just what we discussed. We have in the mass matrix on the right, we have this off-diagonal entry, which is allowed by an approximate Lepton number symmetry. We have only one dominating column of Yukawa couplings to the electron mu and tau flavor. We also have, like with these dots with these 3 dots in the green box, we allow for additional pseudo-Dirac pairs or also additional right-handed neutrinos. And we do this because they may contribute to the light neutrino mass matrix in a way, but we assume that they are negligible for collider phenomenology. So this might be that they're either heavier, that you cannot produce them, or they're very weakly coupled. But nevertheless, we keep this possibility open because otherwise we would run into strong restrictions when we only have a 2 heavy neutral lepton model. So then we get correlations between the different Yukawa couplings, and we would like to keep this still open for collider studies that we can measure these Yukawa couplings independently, and then maybe later on judge if we have a very restricted, very minimal model underlying of this. But in general, we are treating these Yukawa couplings, these 3 Yukawa couplings and this mass parameter as kind of free parameters. Now you have, of course, all the epsilon terms we just discussed in order to explain the light neutrino masses, and they are also included. But now the important thing is when you look at the collider phenomenology, then the details of them are normally not so important, but the only parameter, at least at leading order, and I'm going to explain why this is the case a bit later in my talk, is this mass splitting. So, and that's what we call then the PSPSS, the phenomenological symmetry protected Caesar scenario, where we have as parameter the mass, then these active sterile mixing angles theta alpha, which are proportional to the Yukawa coupling, so these theta alphas, and then one additional parameter, this is this delta M. And this delta M basically captures the effects of this symmetry breaking. Well, it's this breaking of this Lepton number-like symmetry. Okay, and this is the scenario I'm also then going to discuss a bit later in my talk when it comes about heavy neutrino-antineutrino oscillations and understanding Lepton number violation. Okay, so let us now turn to present constraints on the parameters of the heavy neutral leptons and also future sensitivities. And I'm going to discuss this first in the symmetry limit, because actually most studies that have been performed so far either assume the symmetry limits of the Dirac HNLs, or they also assume a single Majorana HNL. And what we're discussing is closer to the pure Dirac case. So we are going to assume this in the following and show the corresponding constraints. So let us go through the parameters once again very briefly. So we see here, this is the Lagrangian I've already shown when you assume the symmetry being exact. So we have this optimal mass term, the one column of Yukawa couplings. So these are the 4 parameters that we have. So now after electroweak symmetry breaking, we have to diagonalize this 5x5 mass matrix. About the naming, we are calling the mass eigenstates the light and the heavy neutrinos that you get out of this, while the neutrinos in the Lagrangian are the active and the sterile ones. So the active are the ones in the lepton doublets, and the sterile ones are the ones which are completely uncharged under all standard model symmetries. And going from one basis to the other defines a 5x5 mixing matrix that we call U. So it is given like this here up to second order in this theta parameters, so which are usually small, like electroweak times Yukawa over mass of the heavy neutral leptons. And yeah, now instead of these Yukawa couplings, we are mostly using these theta parameters, actually, these active sterile mixing angles, in order to show sensitivities, for instance, for collider switches. Okay, so how do these heavy neutral leptons interact? Well, here this upper right block is very important. It contains these theta parameters directly, and it shows how the sterile neutrinos mix with the active neutrinos, as the name active sterile mixing angles also indicates. And because of this active sterile mixing, these heavy neutrinos interact with the charged, with the electroweak interactions. So in particular, if you have a W coupling to heavy neutrino, then this parameter theta alpha governs the coupling of W at the N and a charged lepton of the flavor alpha. So also when you have processes like this at colliders, then you are sensitive to this theta alpha parameter. Then also the C boson couples to the N and neutrinos proportional to this theta alphas. But since you cannot measure the flavor of the neutrino, it will just leave the detector. One is usually summing over the final states with the different flavors. Then this gives you sensitivities to the sum over the theta alpha squared. And also the Yukawa couplings, they depend on the Yukawa couplings, so the couplings to the Higgs, the sterile neutrino and the neutrinos, they also depend on the theta alphas. When you can just rewrite the dependence on the Y alpha, on the Yukawa couplings in the theta alphas. But again, here you cannot really be sensitive to the theta alphas individually, because you always produce a neutrino which you cannot detect its flavor. So these are the interaction vertices. You have them for the production in this minimal scenario where you have standard model plus some sterile neutrinos, some HNLs, but you also have them for the decay. And you can imagine that when the neutrinos are lighter than the W, then they can only decay via off-shell messenger states, and so you can have them potentially long-lived. And this is something which gives very nice signatures. And if this is the case, is illustrated on this plot here, where we show in a plot having the mass m on the x-axis and theta squared on the y-axis, we show c times the lifetime. And you can see that when you're below this brown curve, for instance, you have c tau at the centimeter region. So you have macroscopic displacements, and these displacements are in the laboratory frame, of course, further boosted because they can receive a factor of gamma, essentially. And if this gamma is large, then you have even more displaced vertices. And in fact, these are very nice signatures that have also been searched for at the LHC. And these are results from CMS, where they show the limits that come out of these searches. So far, none of these displaced vertices have been found. And this bound here so you can show the mass. This is now here called Mn on the x-axis. This is what I called capital M before, so the mass of the heavy neutrinos. And on the y-axis, you show the active sterile mixing angle, actually, or the entry of this mixing mass matrix with the flavor E on the left and with the flavor mu on the right. So you see it's a bit more sensitive when you have muons in the final state, and this uses processes with the case into 3 leptons. So you can, for instance, go into a charged lepton and a W, and then go in the lepton in the neutrino. So this is possible at the LHC. Okay, so these are in fact the best sensitivities that one can have for sterile neutrinos. They go down about roughly 10 to the minus 7 almost for this parameter theta squared, the active sterile mixing angle squared. When you want to search for them at higher masses, then precision experiments become very important. And for instance, electroweak precision observables give you constraints on these active sterile mixing angles, but also charged lepton flavor violation is very sensitive. And here is from a global fit, you can see constraints on this. So they're particularly strong for the theta mu, but then also for the theta e, theta tau is the one that is least constrained by the precision experiments. And at least when you're here, look at these lines in the on the constraints for the theta parameters. So they basically extend flat also to the right to very high right-handed neutrino masses, up to the scales where then the Yukawa couplings become non-perturbative. So you have quite some sensitivity to very high scales, while this precision observables, whereas collider experiments at the moment give the best limit for displaced vertex searches. There are also some intermediate results for constraints, also from Atlas and CMS, but they have to be taken with some caution, because they normally assume lepton number violation in their final states. And we are going to discuss a bit later that this depends on some conditions, and I'm not going to discuss them at this stage. All right. Now, what are the sensitivities to properly HNLs at future collider experiments? And there are several colliders that are under discussion. And just they can come in linear form and a circular form are discussed. And in this FCC-EE design study, for instance, 3 versions have been discussed: in a plus minus, a proton-proton collider, also an electron-proton collider. And then what is also discussed very recently a lot, these are muon colliders. And for all of these studies have been made, and people have thought about sensitivities. And indeed, one can probe HNLs much further in the parameter space than this is possible at the moment. And for a discussion, I will focus on the FCC-EE sensitivities, but of course one can also discuss them for the other proposed colliders. So at the FCC-EE, with this 3 versions or 3 modes, the A plus minus, proton-proton, electron-proton, they have different benefits for different ranges of masses, as I will now discuss. So in particular, the best sensitivities can be reached by an E+, E- collider for masses lower than the W mass via displaced vertex searches. So the main benefit here is that you can produce the right-handed neutrinos, so the HNLs, from a C-pole, well, at the C-pole, by then discussing into them and a light neutrino, and you can produce up to 10 to the 13 C bosons at an FCC EE, and this gives you an enormous statistics in searching for the produced heavy neutral leptons. So you can go down almost up to 10 to the -11 in the theta squareds. When you can, when you remember at the LHC at the moment, you can go down almost to 10 to -7. But here you can go up about 4 orders of magnitude, so more than 4 orders of magnitude further down in sensitivity. Also, the FCCE will be very good searching for with electric precision observables for the higher mass range. And where you can also be very good at the FCCE would be at this intermediate region, where at an EP or the PP colliders, you can look for lepton flavor violating channels, which of course then also compete with the other lepton flavor violating experiments, but you can have very good sensitivities and even better than the ones shown here. So there have been some more recent studies from our group also, which you can see listed below, where we show that you can actually do much better with lepton flavor violating searches, also going to higher masses, but also with the processes that are shown here. So the curves are actually better than we estimated at that time. So you can also reach about 10 to the -7 or so. But for higher masses, then that's currently possible. All right, so let's now come to the main part of my talk, where I would like to discuss how one can understand lepton number violation for pseudo-Dirac HNLs. And this is possible with the phenomenon of heavy neutrino, antineutrino oscillations. So let me first explain what this is. So let us consider this process here at the LHC, so, or in general for proton-proton colliders, where you produce out of 2 quarks a W, and then this W, as I already discussed, can decay into the heavy neutral leptons and charged leptons proportional to this parameter and to active stereo mixing angle theta alpha. And about the names that I'm going to use, so I will call this a heavy neutrino N when it's produced together with an antilepton. And I will call this a heavy antineutrino N bar when it's produced together with a lepton. So these two are interaction eigenstates that are well defined by their appearance together with a charged lepton or antilepton. But they're not mass eigenstates. They're superpositions of the 2 mass eigenstates that I call here N4 and N5. 2 different superpositions as I've listed here. So now you can continue when after they've been produced, you have the 2 mass eigenstates propagating, and because of the small breaking of the lepton number symmetry, these epsilon perturbations, we have a small mass splitting between these 2 mass eigenstates. So they will propagate and they will interfere, and because of this mass splitting, they will develop oscillations between this N and N bar states. Very similar to, as you also know it from meson and anti-meson systems, where you have the oscillations of B into B bar or K into K bar. So now they're going to be oscillating, and dependent on the time that they live, they will be either in an N or in an N bar state or in a mixture of both. Now, what is important is that at some point, the heavy neutral leptons are going to decay. And when they decay and they are in an N state, then they produce a charged lepton, like a muon. But when they are in bar state, then they will produce a charged antilepton. And so, depending on whether you have oscillated or not oscillated, you have same sign or opposite sign leptons as your final states. So whether you have lepton number violation or conserving depends on whether these oscillations have been taken place. And this depends on the lifetime of the heavy neutral leptons. So you see an oscillating pattern of lepton number violating and lepton number conserving events in your detector. And that's what we call heavy neutrino, antineutrino oscillations. All right. So we looked at this recently in some detail in quantum field theory, which we think is a good formalism to study this, because it allows you, on the one hand, to give an accurate description and a reliable description of the oscillations, but then also to calculate explicitly possible decoherence effects. And the decoherence effects I will come to also a bit later in my talk. They can have a big impact on whether you can see lepton number violation or you cannot see it in your experiment. So what is this formalism doing in quantum field theory with external wave packets? So you're looking at the usual transition from initial to final states in quantum field theory, but now instead of plain waves, you're considering wave packets. And then with these wave packets, you can have a contradiction-free description of neutrino oscillations, which is important. With plain waves, this is not really possible. You don't even have a notion of position. You just measure your momentum very well. So this is the formalism that we used. So the oscillation, we calculated full oscillation formula. We looked at decoherence. So these full formulae are a bit lengthy, but what is very instructive is to expand them in our benchmark model in the SPSS and to look at the leading and next to leading order contributions there, where we expanded in small quantities, basically in these epsilon parameters. So in the leading order, you can see this first term here, and it depends, or like the upper one is the oscillation probability, and the lower one is the survival probability. So you see, so this upper line, the leading order, it depends only on these thetas. So these thetas are calculating from the leading Yukawa couplings, and then it depends on this 5, 4, 5, which is basically the oscillation length, and this is given fully in terms of the mass splitting. So the mass square differences between the two HNLs, and this is this parameter delta M I was talking about. So these are the leading order effects, and then the next leading order effects, they now start depending on the small parameters. So here, this is this I, for example, and if you look at this I beta or I alpha, it's given on the rest. On the right, it depends on this theta prime, and this theta prime are the suppressed theta parameters that are also 0 in the symmetry limit. And then you can go, of course, further and in the next order, but also this next leading order effect is actually pretty small, at least at the benchmark models that you can test at the high luminosity LHC, and which we have looked at so far. But first of all, yeah, the good news is that the leading order disagrees perfectly with the results that have been obtained also by other groups using quantum mechanics, and this is very good because all these results are now basically re-derived or justified with quantum field theory also, and there are also some very nice works that were done from people at your university that came to similar results with different formalism. Let us look at the leading order, next to leading order terms here in a bit more detail. So what this gives us, this probability for getting a lepton number violation, so this oscillation probability to change from an n into an n bar, and this is just, it has the oscillation lengths given by the 5, 4, 5, and then it oscillates between 0 probability and probability 1 after some certain lengths given by this oscillation lengths. And this is this leading order term, basically. Then this next to leading order term, this is interesting because it gives you, on top of these oscillations, some small modulations which can be identified as flavor oscillations. They depend on the one hand on the parameters of the PMNS matrix. So on this additional Majorana phase, for instance, has some impact. You can realize it's a flavor oscillation because this oscillation remains when you sum over lepton number conserving and lepton number violating terms. It's still there, but it then goes to 0 when you sum over all outgoing flavors. So it is a very small flavor oscillation modulation, but as you can see, when you look at the plot, we have magnified this by a factor 10 to the 7 in order to make it visible. And this is for a parameter that is something that we could see with the high luminosity LHC. Of course, these effects get bigger when you go down to smaller theta squared. like that you approach more the small coupling limit, then also this expansion gets, so the epsilon gets bigger and more important compared to the leading term. Then this effect could also get bigger. So that's something potentially interesting for the FCC-EE, but not really visible, one should think, for the LHC. Okay, so this is like a leading order effect is this oscillations NNN bar, and then on top of this, very small flavor oscillations. Okay, so let us talk about collider signatures that you might hope to see also at the luminosity LHC. And the probably most fascinating and most stunning signature would be if you could actually resolve these heavy neutrino-antineutrino oscillations. So you see really this modulated change of lepton number violation and lepton number conservation at the collider. And okay, how would such a signature look like? And first look at the idealized case that is shown here, where you have for a certain benchmark model, you're fixing the gamma factor to 50, so the right neutrinos all have the same velocity. We look at in this benchmark model also at the delta M that is predicted for a minimal linear seesaw with an inverse neutrino mass hierarchy. So if you remember, so in this case, we are assuming that we only have 2 HNLs, and then this delta M is really predicted. So this is a minimal model, but it's justified from this example that we use this delta M. And then interestingly, with this, you get a quite large oscillation length of the order of 10 centimeters. And so it could look like this, for instance, in LHCB's Velo vertex locator. And you also see that the total number of events goes down because the neutrino decays. So this is just the decay curve. And then what does this different colors mean? So we have the process that we go from 2 protons into 2 opposite sign or same sign leptons, and then 2 jets. And if you look at a certain distance, then the fraction that is in orange shows you the fraction of events that are lepton number violating, and the part and the fraction that is in blue shows you the number that is lepton, the amount or the ratio that is lepton number conserving. And when you see you start at 0, then all the events would be lepton number conserving, and then after about 5 centimeters or so, all events would be lepton number violating, and again at about 10 centimeters, everything lepton number violating, and so forth. So you see at a function of the displacement where this decay of the HNS takes place, you either see you see this oscillating probability of being lepton number conserving or violating. So that would be really an extremely nice signal. Of course, this is not fully realistic yet at all, because we have fixed the gamma factor first of all, and then we just plotted the oscillation formula, how it could be in ideal situation look like. Okay, so the next thing the first thing we of course have to do is we have to care about this gamma factor, because even if you want to look at the LHCb, then this comes in the detector with the distribution. And we see here the Lorentz factor as a function of the polar angle, so the angle with the beam axis. And it can indeed be quite high. So this 50 is not really unrealistic, but it comes in a distribution. And if you would then just plot the oscillations as a function of the vertex displacement, then this would completely smear out the oscillation. So the oscillation length would be different because it's proportional to this gamma also, and then the oscillations would be smeared out. So in experiments, you have to really measure the gamma factor, so you reconstruct it from the final state momentum, and then you plot everything as a function of the lifetime, because this is actually the parameter on which the oscillations depend. But from this reconstruction, you introduce an error. And so the first estimate that we did at this time in 2017 was we were taking an estimate for this reconstruction of the gamma factor from the literature, motivated by the literature. And then we are introducing this error for the reconstruction, and we plotted how the oscillations would look like, including this error. And you can see that for the first 2 oscillations, it actually looks pretty good. But then the error starts to get bigger, and it basically smears out the oscillation pattern. But nevertheless, it looks like for at least this parameter point, you have a quite good chance to really see the oscillations at the LHCb for the high luminosity LHC. So you need enough statistics. And this time when we were doing this was a benchmark point that was not yet tested at the LHC. In the meantime, the constraints got stronger, and this is already tested. But so then we did more recently, we did a more sophisticated study. This one here, where we now wanted to do everything at the reconstructed level. So the first one was just a rough error estimate, but now we wanted to do a real analysis. And the first thing we had to do is we had to find a way to simulate the oscillations really with MatGraph, because MatGraph in its standard version cannot simulate oscillations. So we introduced a small patch, which is also public, so you can look it up. The link can be found at this paper here, where we show how to use MatGraph to simulate these oscillations. Basically, we use the oscillation for the displacement, and then in this displacement we were kind of introducing then the oscillation formula. So we can just simulate events, and we will see immediately after it has traveled a certain time, it gets a displaced decay. Then we see it, and then we find with the right probabilities if this is now lepton number conserving or lepton number violating. So okay, this we can do. Then we of course use the usual tools with PCR and Delphos fast detector simulation to look at, is it possible to see these oscillations in a reconstructed analysis. And we did this for the luminosity at LHC again with 3 inverse Autobahn. We used the CMS detector there, where we had a Delphos card that we could use. And we found that for this benchmark model that we looked at here, so for this benchmark scenario, we could indeed have a 5 sigma discovery. So we also did a statistical analysis from first principles, where we tested this against a non-oscillation hypothesis, and you could really have a chance to discover this, at least that's according to our analysis, possible even at the 5 sigma level. All right, so this is this possibility at the LHC in order to resolve the oscillations, which would be really fascinating, I think. But it's also important to point out that even if you cannot resolve the oscillations, it is extremely interesting because it nevertheless gives you, or the oscillations answer you whether you can observe lepton number violation for these pseudo-Dirac heavy neutral leptons, because these oscillations are the source of the lepton number violation or observable lepton number violation in this scenario. So what you can do is the following. Even when you're not resolving it, you can just say that you integrate over these probabilities from a certain time, let's say time 1, time 2. You integrate over the numbers of same sign over opposite sign leptons that you produce. So and this gives you then the total numbers of lepton number, violating over conserving events. And when you do this integration from 0 to infinity, which is also something you have to think about a bit, because in a real detector, you cannot start with 0 and you cannot go to infinity. But if you do this in the ideal case, and you also assume that you have no decoherence, then you just integrate with this oscillation formula, and you come to this very nice simple formula that this parameter is usually called RLL. It's just given by the mass splitting squared over 2 times the decay rate squared plus the mass splitting squared. So very nice simple formula. And you can interpret also nicely what it means to have observable lepton number violation in terms of the heavy neutrino-antineutrino oscillations. So, okay, first of all, what it means when you have a larger delta M, a larger mass splitting, then it means that the oscillations become faster, right? So the oscillation length becomes shorter, oscillations are faster. And then, so these oscillations, in order to see lepton number violation, they have to compete with the decay of the heavy neutral leptons. So let's assume we have a certain decay length, and then the oscillations are very slow. So this this delta M is very small. This means you have very slow oscillations, and then you have the scenario that the heavy neutral leptons, they oscillate, but the oscillations are so slow such that they cannot oscillate before the decay, or almost not oscillate. Then you have a very small lepton number violation. It can be approximately 0. And that's the case where delta M is much smaller than gamma. Then this RLL is practically 0, and you will have no observable lepton number violation because the heavy neutral lepton or the heavy Neutrino-Antineutrino oscillations are too slow. Then, on the other hand, if this delta M becomes larger, then you see oscillations at some point starting in this time where the decay takes place, and then the lepton number violation becomes non-zero. You can also have some non-trivial RLL ratios when the oscillations are basically just starting, and then the decays happen. And then in the other extreme, when the delta M becomes very large for a given decay rate, then you have very fast oscillations. You have many, many oscillations before the heavy neutrino decays. Then these oscillations kind of average out. And from this averaging out, you will have the same number of lepton number violating and conserving events. So this RLL ratio is becoming 1. And this is then also the limit which you would get when you have just one single Majorana H and L, then it would also give you the same ratio of lepton number violating over conserving events. So in this picture, even if you cannot resolve it, the heavy neutral lepton oscillation, heavy neutrino, antineutrino oscillations help you to understand when lepton number violation is possible or is possible to observe. Okay, there is one thing we looked at recently, and these are decoherence effects. And they can have a strong impact on this ratio, on this RLL ratio. And so we've calculated this in the formalism of QFT with external wave packets, and effectively you can introduce the resulting damping from this decoherence as an extra term, an exponential term, suppressing this cost term in this oscillation probability, as we've shown this here. So this lambda parameter is governing the oscillations, and if this is becoming very large, it's suppressing the oscillations. And in this paper that is shown here, we've calculated this damping parameter. It depends on the mass splitting. It depends on the theta, and one can then now study what it would do for this RLL parameter. And this is illustrated in this plot here. So where you can see, first of all, here in gray, you see the excluded region here, in this dark gray by the LHC. So this is this bound that I've just shown you. And then you can also see in the shaded region, you see some other constraints from colliders, which have partly used lepton number violating observables. Now we have this colored bands of lines, and these are going from the lowest to the highest. So the lowest ones are for the linear seesaw, which has the smallest mass splittings. So the smallest one is for the inverse ordering in the minimal linear seesaw model. So this is the dashed one. Then comes the solid one for normal ordering, and then you go from the different mass splittings for the inverse seesaw, where we just took 3 example values, 5 times 10 to minus 2, 10 to minus 3, or 10 to minus 4, which are these upper lines here. And what is shown here is in colored is the results that you get when you include the damping from decoherence. And in these gray outlines, these are the ones when the decoherence is neglected. And what do the different colors mean? Actually, when you look at one of them, then this brown color, so this is the lowest one, this shows when you're below the brown color, you will have an RLL which is larger than 0.9. So below this, you see large lepton number violation. In between these lines, you see RLL ratios, so ratios between lepton number violating and conservation from 0.1 to 0.9. And above this highest line here, this dark blue line, you have something with, you have a ratio smaller than 0.1, then it starts to get suppressed. And in fact, when you look at this line for the inverse seesaw, so the linear seesaw line, they are not affected by the damping, but these inverse seesaw lines, they get pushed up quite a lot by many orders of magnitude. And this is because of this damping setting in. And it means that you can also already below these lines, you can see, or in these bands, you can see lepton number violating effects, and they start at much larger theta squareds than one would normally estimate without including these damping effects. And this, in a sense, is important also for future colliders, let's say also, for instance, muon colliders and others that can go down to 10 to -7 roughly. Then they have a good chance to see. I mean, if they would discover right-handed neutrinos, then they would see lepton number violation, but it's model dependent. So it would be there for kind of some of the CISO benchmark lines, for instance, while for others it might not be there. And also for the linear CISO, these lines are much lower. So it is model dependent, but within a given model, it's strongly affected by the damping effects. And I see I'm probably running a bit out of time, right? So I should stay within 1 hour. So is it okay if I go for maybe 5 more minutes or
yes,
so?
yes, there is no issue.
Okay, good. All right. So then maybe briefly, I would like to talk also about another topic. These are heavy neutrino-antineutrino oscillations at the FCCEE. Okay, so far we've discussed the oscillations when you produce the heavy neutral leptons together with a W, kind of from a W and a charged lepton. But at the FCCEE, at the C pole, the situation would be different. You would produce them from a C together with a light neutrino. Now at the light neutrino, you cannot see the, or it will not be detected. So you don't know if you have produced an antineutrino or a light neutrino. So you don't know really if you have initially produced a heavy neutrino or a heavy antineutrino for sure. Nevertheless, these will undergo oscillations, and then very similar as we have discussed before, they can, whether they've oscillated or not, they will either decay into a charged lepton or a charged antilepton, and a W, and then this W will go into jets, let's say. So we have these oscillations, but there's a difficulty that you don't know initially if you produce an N or an N bar. But what you nevertheless have is, depending on whether you have a light neutrino or antineutrino, this will give different distributions or probabilities to have the production of an N or an N bar, depending on the angle with respect to the beam axis. So you cannot make statements by looking at the total number of events, but you must look at final state angular distributions. And in fact, in this case, when you have the HNLs coming from the C as an E plus E minus collider, like from the C pole, then it is known that the C is going to be polarized, basically due to parity violation, and you have a forward-backward asymmetry because of that for producing N's or N bars. So more specifically, you will produce more N's in the forward direction, and you will produce more N bars in the backward direction. This is like a 15% polarization of the C, but this will give such a forward-backward asymmetries. And now when you have the N bar oscillations, then you will have an oscillation on top of this forward-backward asymmetry. And this gives also some quite nice signature that you can look for at an FCCEE. And this is interesting because, I mean, with this, with having to rely on this angular, or in this final state angular distribution, it gets a bit more difficult. But you have this very high sensitivity and this very large number of events that you can get at an FCCEE, which, as we found, is also giving you very good sensitivities for resolving these oscillations. So how it could look like is illustrated here in the following. So we see as an observable the HNLs that decay displaced into either a lepton or an antilepton. Now these are charged lepton, antilepton, so specifying whether this have been N's or N bars. And you can see for different benchmark models, you can see in the different colors. So the color means that you're decaying with a higher probability into leptons than antileptons, and the red means that you decay into higher leptons in higher probability in antileptons. And on the very left plot, and you see this given as the angle with respect to the beam axis, And then also the radius here, this is giving the lifetime of the HNL. Okay, so on this plot here on the very left, you have the situation that you have a very small delta m, so you have almost no oscillations taking place, and then you just see this forward-backward asymmetry. So in the forward direction, you have more L's, more leptons. This means more heavy neutrinos, and in the backward direction, you have more N bars, and you produce more antileptons. Okay, now if this so this would be actually the case where it looks very much like a pure Dirac HNL in this limit. Now you have, when the oscillations set in, then you see this second benchmark model here, for example, and then you see when you look in a certain direction, then you see an oscillation between blue and red, and then back to blue. So this is this oscillation, heavy neutrino-antineutrino oscillation on top of the forward-backward symmetry. Then if you even go to benchmark model 3, where you have larger delta M, so now you can see a few of these oscillations, then you see this ringy structure, which would be there showing the oscillations that has now really modulated this forward-backward symmetry into ring-like signatures. And then if you go to very large delta M, where the oscillations are now so large that you cannot resolve them anymore, then you see no forward-backward symmetry anymore. It's completely washed out. And this would be then the case where the pseudo-Dirac HNL looks very similar to a single Majorana HNL. So you just have 50% chance of decaying into a Lepton number conserving and violating way, and this would completely wash out this asymmetry structure. Okay, so this would also be a very nice signature and gives you nice sensitivities at the FCCEE. It also actually is a way that you can unambiguously say that you're Lepton number violating, which I think is also important. So when you look at an angular segment here, then you see you really have a change in the number of Lepton number violating and conserving decays. And this is only possible if Lepton number is really violated. Whereas on the other hand, if you would not have any oscillations, in particular for the Majorana case, where you do have Lepton number violation, you see no modulations, you see just some flat distribution, and it's not unambiguously clear that this actually comes from Majorana HNL and not from something else. Okay, that said, I wanted to do a small comparison of benchmark models, but let me just make this one statement that is pseudo-Dirac HNLs, they're actually something in between a pure Dirac and a single Majorana HNLs. These are the benchmark models that are typically used for collider studies. And the parameter that is kind of making the transition between them is the mass splitting, as we just discussed. When the mass splitting goes to 0, then you come to the pseudo-Dirac HNL case. When it's getting very large, you have averaged out oscillations, and everything looks more like a single Majorana HNL. But in comparison to the other two models, it's really can describe the neutrino mass as well. So the other two models cannot do this very, very well. And you can also have this in-between case that you can resolve the oscillations, which I think is a possibility very fascinating that you would be good to include also as a possibility. All right, so with this, I'm already at the end. I have a summary, but this is basically what I've shown also at the introduction. And I can leave this here, and thank you for your attention. Thank you very much.
Thank you a lot, Stefan, for your presentation. So I guess that now we'll take questions. Any question? Okay, Claudio.
Yes, thanks, Stefan. That was a very nice talk. I had some confusion in the beginning, but when you talk about this neutrino-antineutrino oscillations, you're talking about the heavy neutrinos, right? So, and this occurs because they are not exactly Majorana. They are kind of in the limit of being Majorana or Dirac. That's the idea, right?
Yeah, I mean, they're very close to the Dirac case. They have a pretty small mass splitting.
Exactly.
Not exactly degenerate, yes.
Right. So actually this expression that you have there, like delta M over delta M plus gamma or something, reminds me of an expression that, that you get also for like CP violation in neutrinos. So probably this could also, I don't know, I'm wondering if it would be applied to a model for CP violation in heavy neutrinos. And it could have maybe implications of, you know, leptogenesis or something.
Yeah, there is CP violation as well, of course. So we can with this model we can explain the complete light neutrino data. What we see is that these would come only in the next to leading order. So the leading order oscillations would not show this CP violation, and the next to leading order is pretty small. So I think observing the effects of CP violation in the oscillations, I think is not very good prospects, at least not at the LHC. So you would have to go pretty far down at the FCCEE in order to see it. But that's interesting. It has not yet been looked if there are any chances maybe at the FCCEE to really see them.
And the other question I had is about the decoherence. What's the typical decoherence length that you have here?
So the parameter, so that is so what is mainly affected is the mass splitting. So if the mass splitting is becoming above a certain limit, then the decoherence sets in. And how large this is depends a bit on the input that you choose for the external wave packets, but it is roughly in the electron volt area or so. So we have a more detailed results in our paper. I don't have these plots here in my talk, but yeah, this can be calculated. So the main thing is the mass splitting that is affecting this.
So, but in general, it's a much shorter decoherence length than, let's say, on typical light neutrino oscillations, you know, which are thousands of kilometers.
Yeah, this is I think so. So there are different regimes where you can study this. So the distance of the displaced vertex is in the cases that we looked at is not really the problem. So there you don't lose decoherence because you're traveling too long. This would be like this effect of separating of wave packets. They can maybe come in at some corners of parameters, but the main thing is the decoherence starting because of the mass splitting.
Okay.
Surpassing some.
All right. Okay. Thanks. Very nice.
Okay. Any other questions? Okay, so if not, we can thanks again Stefan for his presentation.
It was a pleasure. Thank you.
Thanks, Stefan.
And thanks to you.
See you.
Ciao, everybody. Ciao, Claudio.